Welcome to a lesson with Dr. Powell. We're going to take a look at how we can compute the derivative of the natural log of x. And we're going to use a limit and also the fact that the derivative of e to the x is e to the x. Let's start by looking at a limit computation for this derivative. And we know its result is e to the x. So to get it, we think of 2 points. Two x values, x plus h and x, which are fairly close together. And as h heads towards 0, the slope between the 2 points on the curve is going to limit to e to the x, to the slope of the tangent line at x on the graph of e to the x. Okay, so to get those y coordinates of these 2 points, we just plug into the function. So we get e to the x plus h, and then we plug x in. We get e to the x, take rise over run. So then we're taking a limit as h approaches 0 of rise, e to the x plus h minus e to the x all over the run, x plus h minus x, which is just h. So we're going to be taking that limit. All right, now we're going to think about this for a minute and maybe even replace this h with something. All right, let's think of it as x plus h minus h. That might actually, or minus x, excuse me. That might actually be useful for us as we go. How can we get the derivative of natural log out of this? Well, if we think about it, we can rewrite x plus h and x in another way. We could think of this as being the limit as h approaches 0, and let's write the top down the same as it is. The bottom, though, so we write x plus h as the natural log of something. Well, natural log and e are inverse functions. Natural log of e to the x plus h. So the action would cancel, so it'd just be x plus h. So we're introducing some logarithms in here by doing that. ln of e to the x. But notice, this e to the x plus h and e to the x also occur up here. In fact, this is like the reciprocal of what we'd want. If we think of, think of this guy, e to the x plus h, that being like a. So think of this whole part as being like ln of a. And think of this as being like a w. So this is like ln of a minus ln of w. And this is like a minus w. So that's kind of like talking about like ln of, if we take a reciprocal of this, that'd be like ln of a minus ln of w all over a minus w. And as h goes to 0, that guy will be going to w. A will be going to w. So this is like the limit as, so a is like this whole thing, right? And w's, make sure we know what that is. A is this whole thing. W is that whole thing. But as h goes to 0, a will be going to w. So that's like a going to w. This right here is like rise over run of 2 points getting close together to a tangent line slope of the natural log. In other words, let's suppose that g of x is equal to the natural log function. Then this limit that we just have right here is the reciprocal of this guy, right? The reciprocals of each other. And and this guy right here, this is the derivative of the natural log function right at w if you plug in w. So not only does this limit here go to e to the x, but it also ends up going to the reciprocal of this, 1 over g prime of w. Aren't we interested to know what the derivative of g is? Because g is natural log, right? We want to know what the derivative of g is. So we're interested in knowing what g prime is. But notice something kind of fun. E to the x is w, is it not? That's what we named as w. So w is equal to 1 over g prime of w. This is pretty good. Just take reciprocals of both sides. We got g prime of w is equal to 1 over w. There's our formula. You could stick x in for w or whatever, but that's the derivative of natural log. Derivative of natural log of x is 1 over x. Right there. Thanks for watching.